be presenting is a model I've been working on for about 6 years now. And I call it the changing density model, but it originally started out as a chameleon model because it's based on a model which Curry and Weltman did back in 2004. The model itself is really a general model that you can use to look at any propulsion method you do have. If you, from current propulsion methods to warp driving method, if you can define a concept for a propulsion method, I can model it under this model. The question is, what's a density field? Well, the universe itself is a big density field. You've got matter in it, and we can divide it up into smaller pieces, and even smaller pieces, all the way down to atoms and molecules and stuff. They're all density fields. The difference between a normal density of an object and a density field is that a density field is everything that's within any spherical circle you can draw within the universe, all the way down to the atom. And the key thing with this model is this density field, since it's not exactly the density of matter itself, but what's in that, there's an acceleration component, which means that if one of these density fields is moving, there's an acceleration component that causes this density field to increase without increasing the density of the matter itself that's in that field. And so the density of the energy space and the density of a particle of matter can be logically defined. The fundamental theory, like I said, was done by Justin Curry and Andy Weltman. It's published in 2004. It's called the chameleon theory. A lot of people, when I say chameleon, their eyes roll back in their heads and they quit listening to me. So I took that name off of this model. But it is a mass or field dependent on local matter density. It's a density model rather than a mass model. And what they saw was that if you looked at the density field inside of a mass versus the density field far away from mass, there's a thin shell that they can define around every piece of matter, whether that's a solid piece of matter or whether that's just a piece of space that you've carved out. It still has this thin shell. Has a thin shell of thickness delta R of C, which we call it. And this is the equation for. There's a lot of equations in here. A lot of them I'm not going to go into any great detail, but just point them out. But I just want to point out there's a fundamental theory behind what I did. The force that they have for this theory is given by this equation, where the betas are coupling factors, the reduced Planck mass, the mass that we're often be talking about, and the gradient of that density field around that mass. And what I had to do was go back into these equations and put back the C's and the H bars that they took out because it's a cosmological equation. They just set those to 1, so units never come out right. So for an engineering model, you have to go back and fix units. And when you do that, you can set this field force up to look like this, where this delta, the thin shell thickness, is this big equation here, where you have the density of the mass you're talking about. Curry and Weltman talks about coupling constants, and in their models they set everything to 1, and because they assume they're on the Earth, and there's some unique reason the Earth, these constants are 1. So what I did is I said this thin, densities are changing. Are not just static. Where Curry and Weltman looked at a static model, static density models, and nothing changes. So well, densities actually change. And so I said, what happens if you take a mass and you put it out way out far in the universe, away from every mass, and you assume the universe is accelerating? What does that thin shell look like? And what I found out is that the thin shell actually gets thicker in the direction you're moving. In other words, when you're far in the universe, the direct acceleration is outward, so your thin shell is thicker in the direction that you're moving. What this means is that the energy density in the thicker side is smaller than the energy density on this side. So this difference in energy density is pushing it. And so if you have any model, a propulsion model that you have, and somebody says, well, you violate conservation of energy, I can say no. The energy is conserved in the change of these thicknesses around the matter that you're talking about, whether it's a spaceship or another matter. So all these nutty ideas that people violate conservation of energy, I can say no, they're not. This is And if you note, this is a likeness to the Abercrombie warp drive bubble, where you have the energy density on one side versus the energy density on the other side that's getting thicker on one side versus the other side, where you have expansion and contraction of the space-time metric, which are mostly in the same direction. So there's correlations between this model and normal space-time model. And I wanted to throw this one out. It's a little early, but I want to get here because I got like 27 slides and we're going to get to all of them. But this is actually the warp drive model. If you take the thin shell around an object and you get it moving towards the speed of light, then the thin shell is going to move way far away out in front of it and get real small behind it. Well, since the density of an object gets real large, then the thin shell is going to get real small. So if you're talking about a black hole, then this thin shell is going to be real small, where you're talking about an atom that's going to be far out. So basically what this model has set up, basically, is you've got, if you're going speed of light, you can assume that the density field is fluidic, so you would end up with circular motion around the back end of it. And if you've got these sort of field lines circling no matter, then you can assume that this is exotic matter. And if you've got exotic matter coming off of this in an angular fashion, well, and then you've got a thin shell that's on the order of the thin shells of a black hole, you've set up actually a wormhole right here behind the matter. And since far away you have a similar pattern, but it's not closed, you could say you have an unstable wormhole here. So basically this solves the horizon problem with wormholes, because basically what you're doing is you're creating the wormhole you're in around you as you go faster and faster. Okay, equation now. Here's the equation for the thin shell. What I noticed in the Kerr-Weltman model was that for the Earth, this thin shell was approximately equal to the square root of the Planck length times the radius of the Earth. So there's actually a new way to calculate the Planck length if you want to do that. But for other planets and stuff in our solar system, it didn't work. So what I had to add was a coupling constant related to the environment that you were actually placed in. Because some objects have atmosphere, even if they have atmosphere, it's different than the Earth. So this is basically a coupling to the environment that you're setting. And I can define these coupling constants by this equation. And for any density field, I can tell you what those coupling constants are. Here's a bunch of messes of stuff. Well, here's the key point here is that the density field density now is a function of the accelerator. It's actually the force that's being input on the density field over the Newtonian force, which is this is the force of the local biggest mass that you're near. So really this is the sum of all of them that's keeping this local. But it really comes down to the fact that if you're moving, then you have an acceleration term that increases the density field's density, and it can overtake the actual density that you actually have that's in that field. So the field density can become larger as you move. And again, what I found out is that when you go back to these coupling constant equations, that this coupling constant here, which I call a motion coupling constant, actually is no longer 1. So when you're moving, your coupling constant is no longer 1. You multiply by your density field. And also what happens is that your radial distance is changing. So I call it the radial factor rather than the distance. So what happens is that the density field radius actually gets smaller as you're moving, which Einstein says that as you go towards the speed of light, you get smaller as you're moving. So that correlates well there with what Einstein says. And any model that we do for propulsion has to fit back into a propulsion model. If you can't relate it to what we're already doing, then it's not a good model. So I developed the field density rocket model. So basically you have a rocket sitting, this is a solid rocket motor. Basically the solid rocket motor is represented by this density field. You have your environmental, your atmosphere density around it, and then you have the Earth's density field defined like this. You light your motor off, and what happens? Well, the gas is accelerating through the nozzle, so now you've created a new density field in the nozzle. So now you have two density fields you have to deal with in this model, along with the external models you have to deal with. And then as you, of course, as you start to burn out, you still have the gas here, but the density here is changing, and then once it burns out, you basically back in the same field. I just want to note that the density field is only equal to the object density when static, in other words, not moving. And these are the equations for the density field of the rocket, the changing density of the rocket, and the density field of in your nozzle. Since it didn't have an original density, or it was so small you can ignore it, it's just basically based upon your gas acceleration. The mass of your gas is defined by this, and these were all developed by trial and error. Everything. Your radius of your rocket nozzle, which I'll give you just in a minute. So basically, all this is just your mass, your fine mass of the gas over the radial factor of the gas. So now we go back to the thrust equation, which everybody knows exists here. So your burnout mass is given by your rocket mass minus the exhausted mass. The difference here is that you can define the acceleration by this weird formula here, which has the Planck length in it, by the way. I was trying to stand by the mic. Anyway, you get this weird equation. And actually, I just calculated this equation this year. This phase factor actually is proportional to the change in the thin shell density over the radial factor. I don't define it in my presentation here, but that's really what that means. This is your radial factor, how small the density field is changing for the rocket, and density field of the gas coming out. And I wanted to point out again that this is just the gravitational constant of your nearest largest mass, which would be the Earth. So this is really a sum of all the gravitational constants around, including the rocket itself. And if I get to the last slide, I'll tell you how that's important to the board division. The phase factor for the rocket is just, basically rocket stuff, your velocity of gas, your exhausted mass, your mass flow rate, and then your radial factor of gas is really just your rocket nozzle times the square root of 2. The radial factor of the rocket, however, is this big complex thing, but what I actually found out from doing an example is that it's approximately the diameter of your throat of your nozzle. So I went to Sutton and Ross, which is a Bible for rocket people, took out their solid rocket motor example. They give you all this mess here. I had to surmise the rocket nozzle and throat diameter, but I actually used to work on a very similar missile, so these are actually pretty good numbers here. And then I calculated the burnout mass from what they gave you, the radial factor of the gas based on the formula I had, the phase factor, which I gave you the equation for earlier, and you use that weird equation I gave you before, and you come out with 422.25 meters per second square. However, if you notice that if you take the acceleration to be the thrust over the burnout mass, you get the same equation, but it's because I adjusted this a little bit. But in general, what this means is for conventional rocket motors, because you can't just, if you go into a liquid system and you get that motor on the stand and you don't have this changing mass due to your propellants being exhausted, they're somewhere in the tank off-site. So, but if you go look at this equation, which is just the mass flow rate times the gas velocity, then you find out that all this really means is you're making a little change to the rocket equation. So, and since this is going to always be much, much less than 1 for conventional rockets, I'll throw that away and use the rocket equation. Don't use this. Okay, what does this mean? It means that propulsion can be achieved without mass ejection, because what you're talking about is changing density fields, and since the changing density field is a function of its motion or acceleration, then you set up a system where you have particulate matter inside of a mass that's moving in one direction faster than it's moving in the other direction. Then you can set up a system where you have a net thrust based on this model. And how, as I said that, let's see the density, but there's a catch here. The density change must be a product of the motion of coherent subatomic particles inside the object being accelerated. And the reason why it has to be coherent, if it's just moving in all directions, then you're not going to get a net force. It has to be moving. You have to define what you're moving, move a whole bunch of masses coherently, and set up the system correctly. Plus, the forward acceleration must be greater than the reverse acceleration inside this mass of particular mass. I wanted to point out that this first part in rocket is done by nozzling of the atomic particles in the nozzle, and that the reverse of this is actually true in the rocket equation, because you want the reverse acceleration to be greater than the forward acceleration, because you're expelling the mass out. Why do you want to use small particulates in a system rather than macro system? So I just said, well, okay, you have a submarine or an egg, and you want to shoot a cannon inside of that. So you're shooting a large mass inside here, and it's hitting the other side. Well, over time, you're going to crack your egg, plus you have pressure waves and everything. So you just want to destroy things. And I found a good video to kind of explain this a little bit. Anyway, you start looking at this from a massless perspective. I set these up to look like nozzles on purpose. And so basically you have a mass represented by this circle that's moving. And since it's moving, then it has this density field that takes on this nozzle shape. But it's not moving because it's, you can see it's changing, but it has a propulsion system. So the smaller system here is actually the propulsion system. So then you have these radial factors defined both for your propulsion system and for your vehicle that's actually moving. And I wanted to point out that you could set this up in a way where you're actually talking about the thin shell density rather than talking about this, just for representation. But the acceleration equation changes when you look at the propulsion system. And what I found out was this piece of it, you can actually set the alpha that's here to that, and reduce the equation to something that's much, much smaller. So then you just have an alpha function, which a lot of times will be very close to 1. Your phase factor, which is a function of how this thin shell is actually changing around the mass. Your radial factor, which tells you how your ship is getting smaller as you're moving. Planck length, and then your gravitational function. The question is, when you're looking at propellant models, what's really being accelerated? You can't just assume that it's the mass of the ship times the field acceleration equal to the field force. So just as a mind thing, I said, well, it's going to be something in the order of the ratio of the mass of the field versus the ship mass times the field force. And when you do that, you can define this field mass with this equation, where this is your particular mass that you're accelerating in your mass. I don't think I have a few charts. And times the acceleration, so these were our electrons. So you have a coherent electrons moving at a certain acceleration, and then you have your field providing field acceleration. You put that back into your thrust equation, you come up with this. And then I looked at, these are some actual numbers for using coherent electrons accelerating, so they're pretty close to being about what they are for electrons. But what I see is I've decided that the particulate mass is on the order of 1/1000 times the mass of the ship. Your field acceleration is about your field acceleration divided by 10. Come out in about 20 meters. Basically, the electron masses are going to work. What I wanted to point out from the Voyager standpoint is that since this guy is changing as you leave the atmosphere, or leave the solar system, because when you're at the Earth, or this is G for the Earth, basically, you leave the Earth, you go through more or less of a summation of all the planets and the sun around you, and then as you get outside our solar system, this drops down to the G of the vehicle itself. And what you actually find is these guys actually approach just the normal value you would have if it was just sitting out in space. So even though all this is getting, the field force is getting smaller as it's leaving, it doesn't go away. There's still a force being pushed on the vehicle itself. And to kind of end this is, most people say you can't push on the dash of your car to make it move. I say, well, unless you can modulate the dash density field in such a manner model, use propulsion system. But the key point here is this is not a new propulsion model per se, but it's a way to gauge concepts and theories people come up with for propulsion model. If you can't tell me how your model fits within this thin shell theory that I've come up with, then you don't have a valid model. And that's pretty much it. Any questions?
We have time for a few questions.
Are you actually getting the right results to explain?
I haven't done that. I honestly believe if you can tell me, if you just set up a propulsion system, then I can model it with this and show you what all the parameters are.
Yeah, I don't think it was model what happens to Voyager, but I'm just wondering, that's interesting.
If I had all the parameters, because I got to know size, weight, and things, and define what the distance field of the ship actually is, actually do the model, I just haven't done that.
Just a clarification point is the Pioneer, I think, has got the anomaly of its velocity.
The other thing is, people were doing this when I was a kid. They would do soapbox derbies. They would change the mass distribution inside the car, and it would give them a little edge sometimes. So they did. The other thing is, if you get near a black hole, it becomes interesting.
I've been looking at this model for a long time. I think as you approach the, either approach the speed of light or approach the density of the black hole, this radio factor probably approaches the plank length. It's real small.
I apologize for my ignorance, but I don't know what is the anomaly on the Pioneer or Voyager spacecraft.
Yeah, I can answer that briefly. I've got to talk where I talk about this. Pioneer is not where it's supposed to be every year. If you look at the velocity that it has and all the known forces acting on Pioneer, and compare that, we have lots of deep space probes out there, and we can pretty much predict pretty accurately from year to year where a spacecraft's going to be based on its velocity, its direction, and we have telemetry and all these other things. But Pioneer consistently is not where it's supposed to be. It's closer. Actually, it's accelerating, isn't it? Or is it decelerating? It's hundreds of kilometers short of where it ought to be if you just take distance as velocity times time. And both Pioneer spacecraft are experiencing this anomaly, and so it appears that there is, quote, some other force acting on the Pioneer spacecraft, which are slowing them down, which is not observed on Voyager and other things. And there have been people looking at this for a long time, trying to model this. There have been some recent papers looking at this. Greg, you may be more familiar with this.
There's been recent work funded by the Planetary Society that, I haven't seen the paper, I've seen the review of this, that seems to indicate that it is something inside the spacecraft rather than a fundamental aspect of physics causing this to happen.
Yeah, but it's the thermal generator inside.
There's
Actually, I think they modeled that, and they figured out that was not sufficient.
I was actually done again.
On that before with the Pioneer anomaly. I was one of the people who did that study. My name's Mary Turco. And although you can't conclusively say that it's not some kind of new physics, it's believed that it's probably just some type of recoil mechanism due to the RTDs or their power source. So the fact that we're not seeing them is Voyager means it's probably something with the mechanics.
it's one of these.
But then there's the Galloway flatline. That's another issue.
It's one of these mysteries that you're not going to solve if you work out and work through get to there and Yes.
I guess this is a very naive question, so throw it out. On the naive side of this response, though, I heard you say, well, there's some recoil mechanism inside due to the power source that's causing it to be not where it is. So it's accelerating or decelerating it. So the logical question is, could you figure out how to use that to move it?
It would be a very good power source. The acceleration is so minuscule that it's considered negligible, and it only comes up just barely above the signal noise that you can notice that the paths aren't where they're supposed to be. And just to clarify by the recoil, so you have this is the back of the antenna, and you have the heat source, and some radiation is coming off, hitting the antenna, and then sending it in a different direction, which is causing it to decelerate. So it's the recoil off of the back of the antenna
Oh, okay, I thought it was internal to it, so it's sort of.
But that's what they proved when they put it in your.
It might be, if you consider everything that's, consider the best physics you can, it's certainly a large component of the acceleration, but not everything can systematically be exerted. So it's still an open question.
Well, my argument with this
The case
is,
isn't closed.
my argument is that if you can define why it's accelerating, then I can model it, regardless of whether it's the change in the concept I'm saying or not.
So does your model, predict the acceleration?
That's what I'm saying, is that if I had the right data, I could see, I could put in this model and see if it compared.
The craft is pretty well, you know, there's schematic of the craft and there's math and everything, consistent craft.
I don't get employed, I don't get paid a lot, and I do a lot of other things outside. What I would like people to do is run with this.
Right.
Take this model, take your situation, set it up, and see if the numbers come out right.
Any other questions for Tony? We have time for one more.
One thing about this, it seems like a Newtonian derivation, that looks like you're violating the conservation of momentum.
I say I'm not, because everything is conserved because of this thin shell. If you take a baseball and throw it, the energy you put into the throwing that ball goes into changing this thin shell in such a way that it gets smaller, or I think it gets smaller on the opposite side of direction and larger on the side of direction. So any violation of conservation of energy or momentum is conserved due to the change in the thin shell.
All right, thanks, Tony, appreciate it.